Exercise 2. A charge Q is uniformly distributed over a disk of radius r and axis OZ. Determine the electric field at a point P on the z-axis. First, let's draw out the problem. Here is our charged disk of radius big R and axis OZ. Then we need to draw on a point P at which we want to find the electric field. Now we need to work out how to divide up the disk into tiny chunks so that we can add up the electric field contributions from each chunk. With a disk, it makes sense to choose a ring as our tiny element. If we were to use a tiny square, it would be more difficult to get the limits of where you're integrating from and to. If we use a ring, we can simply integrate in R from the origin to the outer radius. So here is one of the tiny rings of radius little r. The distance of this ring from point P we will call d, and we'll say it is at an angle theta from the z-axis. So although we're using polar coordinates, integrating over r, we would usually integrate over phi in polar coordinates as well, but actually when we go around phi, which would be in the plane of the disk, the distance d stays the same, so we would only get different components of Ex and Ey which are in the plane of the disk. And as we go around phi in a full circle, we would find that all the Ex and Ey components cancel out. So we actually only need to integrate with respect to r. Now, drawing out our electric field vector from a tiny section of the ring to the point P helps us think about the components of the electric field. So I've drawn one tiny section on the ring here, but I could have chosen any section. The electric field vector for that section acting on point P looks like this. We have already said that the effect of all the Ex and Ey components on point P will cancel out, so we are only interested in the Ez component. We can see from this diagram that the Ez component is equal to the vector E times cos theta. Let's first work out some terms which will be useful in the integration. So the charge density on the disk is given by, which is we're calling sigma, is given by the total charge on the disk, capital Q, divided by the area of the disk, pi big R squared. The charge on the ring, dq, is given by sigma times the circumference of the ring, 2 pi r, times the width of the ring, dr. So 2 pi r times dr will give the total area of the ring. Then you times the area by the charge per area, sigma, to get the charge on that ring. The distance of the ring from P, which is d, we want that in terms of r and z, which will look like this. And we also want to work out cos theta in terms of r and z, as we said before, that Ez is equal to the total electric field times cos theta. We can then write out an equation for the electric field at point P due to one very thin ring. And that will be this. To get the total of all the Ez components from all the rings in the disk, we then integrate from the centre to the edge of the disk. And doing that integration gives us this. Following that through and putting the limits in gives us this. Then usually you would want to give the answer in terms of the terms given in the question. So here in terms of Q rather than sigma. So we can sub this in from before, which gives us our final answer in terms of Q. There are now some interesting limits to look at. The first one is if Z is much bigger than R, So point P is very far away from the disk compared to the size of the disk. What do you think EZ will approximate to? So do you reckon 0 to a point charge, to a plane, or to something else? Have a guess. So we could say that looking at the square root in the equation for EZ here, that if Z is much bigger than the R, then the square root is basically going to be the square root of Z. But then that would give the terms inside the big brackets as 1 over Z minus 1 over Z, and the terms would cancel. So that approximation isn't accurate enough. We need to take the next term of the expansion too. Just looking at the expansion of the second term, we first of all take out a factor of 1 over Z to get it in the right form for a Taylor expansion, which needs to be of the form 1 plus something all to the power something else. So we can write it in that form now. And then the Taylor expansion for that would be this. So we can see that taking the first term, which would be 1 over Z, which is what we were initially thinking of doing, it would not be accurate enough. So we're going to take the first two terms in this case, and that's going to give a non-zero answer, so that's going to be accurate enough for now. So putting that into our equation for EZ will give us this, which all cancels down to give this. And that answer is the same as the electric field would be for a point charge. And that kind of makes sense because if we were really far away from the disk and the radius of the disk was very small compared to our distance, it would look like a little dot to us. The second limit we'll look at is that of R being much bigger than Z, i.e. the disk is very large and the point P is very close to it. Have a guess what this will approximate to. As Z goes towards 0, the first term in the bracket in the equation for EZ will dominate, as the second term has a 1 over Z squared in it, which will become tiny very quickly. So we end up with this, which cancels, and then if we substitute in the equation for sigma that we had earlier, the charge per area of the disk, we would get this, which turns out to be the same electric field that you would get from a charged plane. And this makes sense. As the disk gets very large and you get very close to it, it will start to look like a charged plane to you.